Good day, everyone. In this video, we will be starting with section 3.3, which is on expected values of discrete random variables. Now, in section 3.1, we looked at the definition of random variables, and we saw that we have two types of random variables, discrete random variables as well as continuous random variables. Okay, and we emphasized that in chapter 3, we will only look at the properties of a discrete random variable. Now, in section 3.2, we looked at, if we have a random variable x, we looked at the possible values of a random variable x, which is denoted by a small letter. And we have there the possible values within the curly brackets. We also looked at a concept called PMF, or probability mass function, as well as CDF. And we saw how we can construct or define the PMF and CDF using a table, formula, or some graphical illustration. And we also calculated the probability, different probabilities using our PMF or CDF, right? Now in section 3.3, we will be looking at the expected values of a discrete random variable. So if we're looking at this, if we're focusing on random variable x, then we will be looking at concepts such as expected value of random variable x, or the expected value of a function of random variable x. We'll also look at the variance of our random variable, or the variance of a function of our random variable. And obviously from the variance, we can get the standard deviation of our random variable x, or the standard deviation of a function of our random variable. So this is what we'll be looking at in section 3.3. All right, so by the end of this video, you should be able to, but it will be expected of you to be able to define the expected value of a discrete random variable. You should be able to observe that the expected value is a weighted average of all possible values of a discrete random variable, where the weights are the probabilities of those values. All right, and you should be able to give an expression for the expected value of a function of a discrete random variable. So at the end of the video, you should be able to show or prove that the expected value of ax plus b is equal to a times the expected value of x plus b. You should be able to show that the expected value of ax is equal to a times the expected value of x. You should also be able to show that the expected value of x plus b is equal to the expected value of x plus b. Okay, let us firstly consider example 3.14, which says, consider selecting at random a student who is among the 15,000 registered for the current term at Mega University. So let random variable x denote the number of courses for which the selected student is registered for. So we have in the table the possible values for random variable x, which is value 1, meaning the student has registered one course, or 2, where a number of students have registered 2 courses, or we have 3 courses that are registered for 4, 5, 6, and maximum number of courses that a student can register for is 7. All right. And then in the second row, we have number of students, or number of registered students for these courses. Okay, so we have 150 students that registered for one course, 450 registered for 2, 1,950 registered for 3, 3,000 registered for 4 courses, 5,000, almost 6,000 registered for 5 courses, and 2,550 registered for 6 courses, and then lastly 300 students registered for 7 courses. All right, so if you add up all of these total number of students, total number of registered students, this total here in the second row must add up to 15,000. So yeah, 150 plus 450, 600 plus 1,950, 2.5 plus 3,750, 6.3, 5.8, 12,000, plus 2,550, 14,000. Yes, so total must be 15,000. All right, so we have a total number of 15,000 registered students where a selected student can either register for can register for one course or two courses or three courses or four courses, five courses, six courses, or maximum 7 courses. All right. So in chapter 1, we saw that if we had this type of table, and we want to calculate, let's say, the average number of courses that a randomly selected student can register for, we would do the following. So suppose that I redo this table like this. Sometimes it's better if it's vertical. It depends. I'm just writing it down since it's something that you would have seen already from chapter 1. All right. 3,050 for 5, 5,250 for 6, 2,550 for 7, 300. Okay. So we have here the frequency. We have 150 students registered for one course, 450 students registered for two courses, and so on. So to calculate the average number of courses that a randomly selected student can register for, we know from chapter 1 that we can calculate then the total number of registered courses, right, at Mega University divided by the total number of students, right? Or we can calculate the average as follows. So for those that only registered for one course, we have how many? 150 students, right? So say 1 times 150 plus those that registered for two courses, how many are they? 450 students. Plus those that registered for three courses, how many students do we have that registered for three courses? 1,950 plus until those that registered for 7 courses, and we see that only 300 students out of 15,000 registered for 7 courses. So if we then do or sum up those products and then divide by total number of students, then we would have a total of 68,550 registered courses amongst the 15,000 divided by 15,000 students, and that is 4.57. So this 4.57, it's not a possible value of a random variable x. No. It indicates to us where the population of a random variable leans to. So it says that the average number of courses that a randomly selected student can register for is between 4 and 5 courses. And we see with the number 4.57, it means that it leans mostly towards 5 courses. All right, so the average number of courses that a randomly selected student can register for is about 5 courses, 4 to 5 courses. What does this mean? It means that if we draw a bar chart and we have here the frequency, let's say on the y-axis, and the possible values on the x-axis, then it means that for possible value 1, if we have 150 students, for 2, say we have 450, for 3, 1,950, for 4, 3,750, for 5, we have 5,850. That one is mostly popular, we see, as majority of students, 5,850 of them registered for 5 courses. And then for 6, we have 2,550. And then for 7, we have 300. Okay, so we see that the population for our random variable x is centered around this place here, all right? So we're expecting from our calculation that an average number of courses that a randomly selected student can register for, it's between 4 and 5. Where 5 is, I guess, the most popular option here in this scenario, where we see that majority of students registered for 5 courses. Okay, so now still on example 3.14, let's say we want to calculate then we want to define and construct the PMF. So we can calculate then the probabilities of observing those specific possible values, right? So given this information about the number of students that registered for these courses or number of courses, can we calculate the probability that x is equal to 1 or x is equal to 2 or 3 or 4 or 5 or 6 or 7? We can, right? Okay, so if we have here a total of 15,000 registered students, then what's the probability that x is equal to 1? That a randomly selected student in megacity would register for 1 course. What's that probability? Okay, so if we have then number of registered students in this column here is 150, then the probability P1 is just equal to 150 divided by 15,000, right? Isn't that true? Okay, so P1 is then equal to 0.01. And so P2 will then be 450, then divided by 15,000. And so the probability is 0.03, okay? And then P3 is just 1,950 divided by 15,000. And then that is 0.13, and so on. So if we calculate then the probabilities for each of these possible values for random variable x, then we will get the specific probabilities for when you observe x equal to 1, 2, 3, 4, 5, 6, and 7. So if we complete then the PMF table, we will have these corresponding probabilities. Okay, where we can calculate them using the information that we have. For P4 is just 3,750 divided by 15,000. For P5 is equal to 5,850 divided by 15,000, and so on. Okay, P6 2,550 divided by 15,000. P7 300 divided by 15,000. All right, so now we saw that in the previous slide that the average number of courses that a randomly selected student can be registered for is between 4 to 5 number of courses, okay? And we calculated it as, so it's a product of the number of courses times the frequency. So I'm just going to rewrite it again quickly here. Plus 7 times 300 divided by 15,000. All right. So if we break down this product, the numerator and denominator, we see that this is equal to 1 times 150 divided by 15,000 plus 2 times 450 divided by 15,000 plus 3 times 1,950 divided by 15,000 plus 7 times 300 divided by 7 times 300 divided by 15,000, right? So if you break this down and you calculate individually and you split this denominator, then we will see that it's equivalent to this, right? But then what are these fractions equal to? So we have here 1 times 150 divided by 15,000. So that fraction is equal to 0.01 plus 2 times 0.03 plus 3 times 0.13 plus 7 times 0.02. All right, so looking at our table, what are these values equivalent to? They're equivalent to our probabilities, right? Okay, so if we then write it down in a formula way, we have here 1 times P of 1 plus 2 times P of 2 plus 3 times P of 3 plus 7 times P of 7. And so if we write it as a formula, these summation signs plus can be denoted by that. So it's summation sign. And what are we adding? We're adding a product of possible value of a random variable x, right? Times what? The probability of observing that possible value, which is px, and we added them up for all possible values of a random variable x. Okay, so we see that the expected value or the average number of courses here that a randomly selected student can be registered for can be calculated using this table here as in chapter 1. Or if we see that we have the possible values of a random variable x, and we also have the probabilities of observing those possible values, then we can use these two, 1 and 2, to calculate the exact same thing, the average number of, in this scenario, the average number of courses, okay? So if we only have possible values and the probability of observing those possible values, then that's enough for us to calculate then the average number of courses in this case. So this example leads me to the first definition in section 3.3. That says, for the expected value of random variable x, let random variable x be a discrete random variable. Very important, it must be a discrete random variable. In chapter 3, we said that we're only focusing on discrete random variable. So let random variable x be a discrete random variable with set of possible values d, okay. In the previous example, d is made up of values 1, 2, 3, 4, 5 until 7. 1, 2, 3, 4, 5, 6, 7. And suppose that we also have PMF, PX, a valid PMF. And so the expected value or mean value of x denoted by capital E bracket capital X or mu x. So it's mu x is, so the expected value of x is equal to mu x, which is equal to the sum of this product. So you multiply the possible value of x with the probability of observing that possible value. Once you have the product of x and its probability, then you add them all up for all possible values of x, right, in your or possible range of values for random variable x. So it says that this expected value will exist provided that the sum of the product of absolute value of x and its probability of observing those possible values, this sum must be less than infinity, or the expected value of our random variable x